All right, so this should be the last part of section 3.1, and the problem that I'm about to do now, number 24, when we go to do part B, the critical numbers, it's going to be a little bit different than the critical numbers that we did for the first half dozen problems because of the radical. And radicals have domain issues, and there's values of x for which the derivative could be undefined. I'll talk about that in a second. Let me jump into this and get part A done real quickly. Part A wants me to find the derivative. In order to do the derivative, I should probably rewrite the problem without the square root, and square roots can always be changed into problems that have exponents of 1/2. So I'm going to rewrite this as f of x is x minus 5 to the 1/2 power. Now I'm going to use the chain rule to take the derivative. So I'm going to write f prime of x because I'm taking the derivative. I'm going to bring the exponent out in front of the parentheses, leave myself a little room, leave the contents of the parentheses unchanged, and then subtract 1 from the exponent. And instead of writing 1, I'm going to subtract 2/2 from the exponent. So the exponent that's going to belong in my derivative is 1/2 minus 2/2, which is negative 1/2. Haven't finished the chain rule because I haven't filled in the gap where I left myself some room. To finish up the chain rule, you take the contents of each term inside the parentheses. The x term, because it's a first power term, its derivative is its coefficient. There's an implied 1 there, and the derivative of any x to the first power term is its coefficient. So inside the parentheses, I'll put a 1 for the derivative of the x, or the 1x, and the minus 5 is a constant, so it has a derivative of 0. So left myself a small parentheses because I knew all I had to put was a 1 in there. I'm going to clean this up a little bit, meaning I'm going to multiply the 1/2 and the 1, and that will give me a 1/2. I'm going to make the exponent on the x minus 5 to the negative 1/2 positive by bringing it down into the denominator with the 2. And then I'm going to change the 1/2 power back to a square root, and I'm going to go ahead and write my answer right up here as f prime of x equals the fraction that has a 1 in the numerator and 2 times the square root of x minus 5 in the denominator. So I'm going to just do that. All right, so that's the derivative. Now, critical numbers, when I was doing critical numbers earlier, every derivative that we took was a polynomial, and critical numbers are any place where the derivative is equal to 0 or it's undefined. To find the values of x where a fraction is equal to 0, it's enough just to either set the whole fraction equal to 0 or to set the numerator equal to 0. So let me go ahead and try to find the critical numbers quickly here, or as quickly as I can. So the critical numbers for this particular problem are a little bit different. So the derivative f prime of x is 1 over 2 times the square root of x minus 5. What we had been doing is just taking the function and setting it equal to 0, because any value of x where the derivative is equal to 0 is a critical number, and we got that by taking the derivative and setting it equal to 0. To solve this, I'd probably write the 0 in fraction form by writing it 0 over 1, and then I'd cross multiply. Cross multiplying down, you get 1 times 1. Cross multiplying up, you get 0 times the quantity, 2 times the square root of x minus 5. That's going to give me 1 on the left side, 0 on the right side. Since there's no x in there, there's no solution. So just setting the function itself equal to 0 doesn't produce a critical number. But there's two kinds of critical numbers we need to find. Critical numbers are defined as any value of x where the derivative equals 0, and we just found there was no values of x where the derivative is equal to 0, or is undefined. And these are the critical numbers that we're going to come up with when we do this problem number 24. So there's no critical value that makes the function itself equal to 0. But there is a critical value, a value of x that makes the function undefined. Because to find where this derivative is undefined, I'm simply going to take the denominator and set it equal to 0. It's like finding the domain of a fraction. Any fraction is undefined for any value of x that makes its denominator 0. So to get the critical numbers where the derivative equals to 0, there's none of them. So this algebra right here is attempting to find the critical numbers, or the values of x that make the derivative equal to 0. I don't like the way I'm saying that. Here I was attempting to find the value of x where the function is equal to 0. And there weren't any of those. Down here I'm trying to find the values of x where the function or the derivative is undefined. Could have wrote derivative there. So two types of critical numbers, the values of x where the derivative is equal to 0, you set the whole derivative equal to 0, and critical numbers where the function is undefined. Those didn't come into play for the first few problems of this style because all the derivatives were polynomials, and polynomials are defined everywhere. There weren't any values of x where the function was undefined. But fractions can be undefined for certain values of x, and the values of x that make fractions undefined are the values of x that make the denominator 0. So to find the second kind of critical number, we're going to take the denominator of our fractions and set them equal to 0. Here, the algebra is to divide both sides by 2. The left side, the 2's cancel. The right side, any fraction with 0 in the numerator is equal to 0. And then I'm going to square both sides to get rid of the radical. On the left side, when I square it, the squaring cancels out the square root symbol, leaves me with x minus 5. On the right side, 0 squared is 0 times 0, which is 0. And then I'm going to add 5 to both sides. And that's going to give me the only critical number for this problem, which is x equal to 5. So when I go to answer part B, I'm going to say the critical number for this problem is x equal to 5. So I'm going to move on to C, D, E, and F. I'm going to do those on my calculator, then I'm going to do them by hand. Regardless of how I'm getting the answers to C, D, E, and F, I have to understand something about the square root functions. Square root functions have restricted domains, meaning they don't have domains from negative to positive infinity. And the restricted domain is going to show up in my answers to where the function is increasing and where the function is decreasing. And very specifically, to find the domain of any square root function, because it's going to be important here, the original function in problem 24 was f of x equals the square root of x minus 5. To find the domain of any square root, we take the argument of the under the radical and set it greater than or equal to 0. And when I do that, actually I set it greater than or equal to 0. The domain for this fraction is all real numbers greater than or equal to 5, which means when I go to sketch a graph, x equal to 5 somehow is going to be the starting point of the graph, and there isn't going to be any part of the graph to the left of x equal to 5. And that's going to be important. In a second here. So because this has a restricted domain, my answers for the increasings and decreasings might not have all the infinities that I had previously. So now I'm going to jump in and do C, D, E, and F on my calculator, and then I'll confirm my answers by hand. So for C, D, E, and F, my initial function was f of x equals the square root of x minus 5. I'm going to borrow a graph to do 24 C through F. And unfortunately, it's a little bit trickier. I know I need to put 5 on my x-axis because it's a critical number. In addition to it, I usually put positive and negative infinity on my x-axis. It'll turn out that when I go to do C through F, that the graph isn't going to exist to the left of x equal to 5. And there won't be any graph to the left of this. And none of this region is going to show up as a increasing or decreasing interval because there won't be a graph there. Let me go ahead and do that right now. So I'm going to graph the function y equals, clear out the stuff that's in there, then second square root x minus 5. Let me just do a zoom standard. And you can see right here at 1, 2, 3, 4, 5, 0, it looks like at this point 5, 0. It looks like it's the 0.50. I'm going to say that's the 0.50. It looks like that's where the graph starts, and it goes forever up and off to the right. So that's what the graph looks like to me. And when I go to describe the intervals where the graph is increasing and decreasing, I'm not going to have any interval that's to the left of that critical number. When I put that critical number on the x-axis, it broke the x-axis up into the interval from negative infinity to positive 5, and the interval from positive 5 to infinity. And in this first interval from negative infinity to positive 5, to describe what the graph is doing, it's not doing anything because there's no graph here. This is outside the domain. So I can't say the graph is increasing or decreasing in that interval because the graph doesn't exist in that interval. Any interval that's outside the domain, it doesn't have a graph, so it can't be increasing or decreasing. I move over to the next interval, 5 to infinity, and that's just a single interval. Within a single interval, you can't be both increasing and decreasing. You can only do all increasing or all decreasing in an interval. Between intervals, you could change directions. And in this particular interval, it looks like the function is increasing. So it would be very correct to say the function is increasing in the interval 5 to infinity. So I'll come back to part C and write that down. And then there were only 2 intervals because there's only one critical number, and you get one more interval than critical numbers. The left interval, the graph didn't exist, so it can't increase or decrease where it doesn't exist. And the interval 5 to infinity was always increasing, so the interval where it's decreasing, there just isn't one. There's only one interval where the graph exists in terms of the critical numbers that I found in part B. In order to have a maxima or minimum point, you have to have a hump. You have to change from increasing to decreasing or change from decreasing to increasing. This graph is going up forever. It's almost like a graph of a line in some sense. It doesn't change directions, and when a graph doesn't change directions, it doesn't get any, high points or low points, so it doesn't have any maximum or minimum points. So, with that being said, those are the answers. Now let me do them by hand, and I'll pretend I didn't know about the domain. So if I was doing part C, D, E, and F by hand, and I didn't know that the domain of this was x was greater than or equal to 5, I can still get the right answer. And how would I do that? To do C, D, E, and F without my calculator, on a number line, I would put negative infinity on the far left edge, so this is still part 24, C through F. Negative infinity on the far left edge of the number line, positive infinity on the far right edge. The number 5, which is the only critical number on the number line, and then I'd create the interval from negative infinity to positive 5, the interval from positive 5 to infinity. I'd pick a value of x to check in each interval. In this interval, because it goes from a negative number to a positive number, I'd like to check 0 for my test number. In this interval, because it's all positive, I can't pick 0, I'll pick a number that's small that's in this interval, and that's going to be x equal to 6 for me. You could pick x equal to 11 if you care to. Now I need to find f prime of each one of those numbers. And I can do that by just taking the number and plugging it into the derivative. I can go 1 over 2 times the square root of 0 minus 5, or 1 over 2 times the square root of 6 minus 5. And I can do those by hand. I don't care to do those by hand. And it's not real important exactly what the number is. It's only important what the sign of the number is. So because on my calculator I've already graphed the initial f of x function, I could go second calc, go down to dy dx, and type in the number 6 to figure out the value that I get when I plug 6 into the derivative. So this computation right here can be done by going second calc dy dx, typing the number in, and when I type this in, I think I get 5. It's round, at least it rounds to 5, and this is positive. So the graph is increasing in that interval from 5 to infinity, which I already knew. And in the interval where the graph doesn't exist, what happens on my calculator when I go second calc dy dx and I go to type in 0, I think nothing's going to come back. It's when I hit enter, it's going to have a y equals, and it's going to have a blank next to the y equals. When I typed in 6, it came back, oh, dy dx equals, and it gave me 0.5. I missed the decimal there. So it didn't, the fact that I missed that decimal wasn't such a big deal, because I'm only not worried about the number, I'm worried about the sign of the number. So I should have written 0.5 there, hardly that big of a deal, because it's a positive number, the graph is increasing in that interval. When I go to do the same computation, second calc dy dx, and I type in 0, it gives a blank next to the y. Did I do that right? Second calc dy dx, type in 0, and it's just perplexed. It doesn't even tell me dy dx because the derivative is undefined here. So this right here, it's actually an imaginary number. If I did this computation by hand, I'd get f prime of 0 equals 1 over 2 times the square root of negative 5. Square roots of negatives become i's. It would come out to an imaginary number, 1 over 2i square root of 5. So this right here, this tells me that when I plug a number in this interval, I get an imaginary number. This tells me the graph doesn't exist here. I have to physically get a positive or negative real number to know whether the graph is increasing or decreasing. And when I get an imaginary number, the graph doesn't exist there. Although I knew the graph didn't exist there because I knew the domain of this and I sketched a graph. So the only region where this graph is doing anything is this region where it's increasing, because when I plugged a number into the derivative, it came out to a positive number. If I show this on my number line, there's no increasing or decreasing in this interval, and in that interval it's increasing. So you can see it's never decreasing because I never get a negative number out when I plug a number in my from an interval into the derivative. So it's never decreasing. It's only ever increasing, and it has to change directions. I have to get a peak or a valley to get a maximum or a minimum. Because it's never changing directions, I don't get a maximum or minimum. So I can transfer this only answer that I came up with, that it's increasing from 5 to infinity. I don't have any down arrows because I didn't get any negatives when I plugged a number into a derivative. And because it doesn't change directions ever, I don't have any maximum or minimum points. All right, give 23 a go. That's 20 minutes on one problem. That doesn't shape well for the rest of this video. I'm going to move on to do problem 26, and it's another square root. Square roots have domain issues, and they'll come up as I do my work. So let me just do part A of 26. I want to find the derivative, and in order to find the derivative, I should rewrite this problem so that it doesn't have the square root symbol. I'm going to write it as 12 minus 3x to the 1/2 power. I didn't write prime yet because I haven't taken the derivative. And now I'm going to take the derivative. I'm going to write f prime of x. I'm going to bring the 1/2 out front. I'm going to leave myself some room. And then I'm going to leave the contents of the parentheses the same and lower the exponent by 1. And instead of lowering the exponent by -1, I'm going to do -2/2 because that makes it easier to simplify that exponent. 1/2 minus 1 is the same as 1/2 minus 2/2. That simplifies to -1/2. Inside the parentheses that I left myself some room for the shortcut of the chain rule, I'll write the derivative of 12 minus 3x. 12 is a constant, it has a derivative of 0. Minus 3x is a first power term, and first power terms have the derivative of their coefficient, so you get minus 3. I'm going to clean this up. I'm going to multiply 1/2 times minus 3. To multiply those, you just multiply the 1 and the minus 3 together. And I'm going to move the negative exponent term into the denominator with the 2. So f prime of x will be negative 3 in the numerator, 2 from the denominator of the fraction 1/2, and 12 minus 3x to the positive 1/2 by making that exponent, negative exponent positive, will also find its way into the denominator. That's basically the derivative, but I can write it better. So I can say f prime of x equals negative 3 over 2 times the square root of 12 minus 3x. That's just taking the 12 minus 3x to the 1/2 and giving it a radical. All right, so now we can go to part B and find the critical numbers. So for part B, the critical numbers for 26b in section 3.1, the critical numbers are any values of x where the fraction or the derivative is equal to 0, and you get those by taking the derivative, negative 3 over 2 times the square root of 12 minus 3x. You get those by setting the derivative equal to 0. And we also need to find the value of x where the derivative is undefined. And there we set the denominator equal to 0. For the values of x that make the derivative equal to 0, I set the 0 equal to a fraction and cross multiply. If I was being clever, I would have shortcutted this step and just set the numerator equal to 0. But I wasn't being clever, so I'm doing it the maybe proper way. So cross multiplying down, you get negative 3 times 1. Cross multiplying up, you get 0 times the quantity 2 times the square root of 12 minus 3x. On the right side, negative 3 times 1 is negative 3. Left side, negative 3 times 1 is negative 3. And on the right side, 0 times anything is 0. The x's drop out. There's no x when I get to this step, so there's no solution to this problem. So there's no value of x where the derivative is equal to 0. So now I'm going to find the values of x where the derivative is undefined by taking the denominator and setting it equal to 0. I'll divide both sides by 2. On the left side, the 2's will cancel, makes the fraction go away. That will give me the square root of 12 minus 3x on the left side. On the right side, 0 over 2 is equal to 0. Now I'm going to square both sides. On the left side, squaring a square root cancels out the square root symbol, leaves me with 12 minus 3x. On the right side, 0 squared is 0. Now I'm going to add 3x to both sides. And that's going to give me 12 on the left side, 3x on the right side, and then I'll divide both sides by 3, and that will give me 4 equal to x. So the only critical number that I get for problem 26 is x equal to 4. That's a value of x where the function is undefined. So for part B, the answer, the only critical number is x equal to 4. Just had a hitch, so the only critical number is x equal to 4. So now let me do C, D, E, and F on my calculator by graphing this. On my x-axis, I'm going to label 4, negative infinity, and positive infinity. And because this is a square root, it has a restricted domain, and that's going to show up as I do my graph. So the function that we're dealing with here in problem 26 is f of x equals the square root of 12 minus 3x. It has a critical number of x equal to 4, and I'll pretend I don't know anything about the domain, but square roots have restricted domains. Usually you only get graphs on one side of the critical number. So let me go ahead and sketch a graph out and find out where this is increasing and decreasing. So I type my y equals clear second square root 12 minus 3x. Graph it. So the graph looks like that. So it goes to that 0.40 right there and kind of just looks something like that. So the critical number that I put on the graph created two intervals. It created the interval from negative infinity to 4 and an interval from 4 to infinity. In the interval from negative infinity to 4, as I move from left to right, the graph is going lower, so it's decreasing in that interval. And in the interval from 4 to infinity, there's no graph because it's outside the domain of the square root, so it's neither increasing or decreasing. So when I go to answer the increasing and decreasing parts for problem number 26, I'm going to say it's decreasing in this interval. I'm not going to make any comment about this interval because it's outside the domain of the function. If I went to find the domain of this, I'd go 12 minus 3x is greater than or equal to 0. To find the domain of a square root, you set the argument greater than or equal to 0. I'd solve for x by minusing 12 from both sides. That would give me minus 3x is greater than negative 12, greater than or equal to negative 12. And then I divide by negative 3. When you divide by a negative, you flip the direction of the inequality. And this would give me the domain as x is less than or equal to 4, which is exactly what this shows me, that the graph exists only to the left of x equal to 4. It doesn't exist to the right of x equal to 4. So square roots have kind of, half graphs in some sense. So when I go to write my answers, I'm going to say it's decreasing. It's never increasing. So is it ever increasing? No, there's no interval where it's increasing. It's decreasing in the interval from negative infinity to positive 4. And to get a maximum or minimum point, the graph has to change directions from increasing to decreasing or decreasing to increasing. And so there's none for maximum points and none for minimum points. If I didn't have a graphing calculator, well, then I'd have to do horrible work by hand. Even with a graphing calculator, I can get my answers, but this isn't suitable for a test. To get answers C through E for test purposes, so for 26, C through E, the by hand approach, on my number line, I'll pretend I don't know anything about the domain of this problem. I'd put negative and positive infinity on the edges of my number line and the only critical number 4 between them. That's going to create intervals, the interval from negative infinity to 4 and 4 to infinity. In each interval, I need to pick a test number. Because this interval, I go from a negative number to a positive number, I'm going to test x equal to 0. And in this interval, I'm going to pick the smallest number I can that's easy to work with. I'm going to pick x equal to 5. And then I need to take those test numbers and plug them into the derivative. This step right here would involve by hand taking this value and plugging it in for those x's. I don't expect you to do that on the test. To get the value that you get when you plug a number into the derivative, it's enough to use the dy dx feature. So that's what I'm going to do. I have the function in here properly. To do f prime of 0, I'm going to go second calc dy dx, type the number 0 in, and it tells me dy dx is negative 0.433. And because it's a negative number, the graph is decreasing in this interval. So above the interval negative infinity to positive 4, I'm going to put a decreasing arrow. Now move over to my next interval. If I do second calc dy dx and type the number 5 in, I get nothing because it's an imaginary number. It's, in some sense, we can say it's undefined. Technically, you'd get a negative under the square root, which is an imaginary number. And regardless of that, whether you want to consider it undefined or imaginary, that means it isn't increasing or decreasing, because to be increasing or decreasing, I have to get a number out. If it's a real number out, if it's positive, the graph is increasing. If it's negative, the graph is decreasing. So it's neither increasing nor decreasing because the graph doesn't exist here. It's outside the domain of the function. So now I could transfer this to my work here. It's decreasing in the interval negative infinity to 4. I don't have any intervals with an up arrow, so it's never increasing. And these parts, I look at my number line, I don't get two intervals next to each other where the graph changes direction, so it's never given me a maximum nor a minimum point. All right, so give 25 a go. Still 4 more problems to do, and the next one's a fraction. Fractions also have domain issues that we have to worry about. So when we go to do problems 27 and 28, we'll have different issues but similar issues to square roots. So first part of 28 is to do the derivative. So I'm going to go f prime of x. I don't need to rewrite it. It's ready for my derivative. And it's a fraction, so I'll do the quotient rule. The quotient rule, you start off by taking the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So this is kind of the shell for my derivative. It's a denominator times derivative of the numerator. I haven't taken that derivative yet. Minus numerator times derivative of the denominator. I haven't taken that derivative yet. I'm going to take the derivatives I need to take on the next step. So on the next step, where I have the DER's derivatives, those are going to go away and be replaced with what the derivative is. For x plus 3, the derivative of that factor, x is a first power term, its derivative is its coefficient, so the derivative of x, part of that parentheses, is 1. The plus 3 is a constant, it has a derivative of 0. So the derivative of x plus 3 is 1. I bring my minus sign down, I bring the x plus 3 down, and I think before it as opposed to after it, I'm going to write the derivative of x minus 7. The derivative of the minus 7 is 0 because it's a constant. The x is the first power term, so its derivative is its coefficient, and its coefficient is 1. So to the left of that parentheses, I'm going to write a 1, which is the derivative of 1x minus 7. The denominator is still x minus 7 squared. Now I'm going to clear the parentheses. Both parentheses are just multiplying by 1. So I can say this is equal to x minus 7 times 1, which is x minus 7, minus 1 times x plus 3, which is x plus 3, over x minus 7 quantity squared. I didn't drop the parentheses, but I could have. Now I'm going to drop the parentheses. I'm out of room going lower, so I'm going to go horizontal. This parentheses, when I drop it, it's just going to stay in x minus 7. This parentheses, when I drop it, I'm going to get a minus x and a minus 3. I'm going to leave the denominator x minus 7 quantity squared. In the numerator of the derivative, the x's cancel, and you're left with a minus 7 and a minus 3 that combine to minus 10. So my derivative is going to be a fraction. The numerator is going to have a minus 10. The denominator is going to have x minus 7 quantity squared. So f prime of x is going to be minus 10 over x minus 7 quantity squared. To find the critical numbers, I want to find the values of x where the fraction is equal to 0 and the values of x where the fraction is undefined. So I'm going to do part B by hand, but on another piece of paper. So for part B of 28, the critical numbers, the derivative f prime of x equals to negative 10 over x minus 7 quantity squared. I'm going to find the values of x that make the derivative equal to 0 by setting the derivative equal to 0. So I'm going to go negative 10 over x minus 7 squared equal to 0. And I'm also going to find the values of x that make the derivative undefined. This derivative is a fraction. Fractions are undefined for any value of x that make the denominator 0. So when a derivative is a fraction, the values of x that make the critical numbers I get that cause the fraction or the derivative to be undefined are the values of x that make the denominator 0. This is going to have no solution. Just like I did with the last derivatives, I can make this into a fraction and cross multiply. Negative 10 times 1 is going to be negative 10, and 0 times x minus 7 quantity squared is going to be 0. There's no solution because the x's drop out here. Generally, when you're trying to find the values of x that make a derivative 0, and if the derivative is a fraction, it's enough just to set the numerator equal to 0, because when you cross multiply, that's what it turns into. For this part right here, I'm going to square root both sides. Usually I need to plus or minus when I introduce a square root into a problem, but because the right side is 0 and positive 0 and negative 0 are both 0, I didn't insert the plus or minus sign. On the left side, I cancel out the exponent. That leaves me with x minus 7. And on the right side, the square root of 0 is 0. So the only critical number I get is x equal to 7. Unlike square roots, the graph will exist on either side of this critical number. So for my critical number, it's going to be x equal to 7. And let me move on now and do C, D, E, and F by hand. I mean by my calculator, then I'll confirm them by hand. So for C through F on problem 28, I'm going to put negative infinity on the far left edge of my number line. The only critical number 7 on my graph instead of number line, and positive infinity. So this is going to break up the graph into the interval from negative infinity to positive 7 and positive 7 to infinity. I'm going to graph my function f of x equals x plus 3 over x minus 7 and figure out the intervals where the graph is increasing and decreasing. So on y equals clear parentheses x plus 7 divided, x plus 3 divided by parentheses x minus 7. Zoom standard should be fine for this graph. And this graph has a big old break. At x equal to 7, the graph doesn't exist because it's outside the domain of the original function. So this graph, if I look at it, I don't have the best picture, but I get a vertical asymptote at x equal to 7. And to the left of x equal to 7, the graph looks something like this. And to the right of x equal to 7, it looks something like this. You can barely see this, so I should probably blow my window up a little bit. Let me make my x's go a little bit farther to the right, say to 20, and make my y's go a little bit higher, say to 50, so you can see this right side a little bit better. So the break right here is at x equal to 7, and then you get a left side that looks something like that, and a right side that looks something like that. So in terms of increasing and decreasing, from the graph, it should be easy to see that in this region right here, as I move from left to right, the graph is going down. So that's going to be a decreasing interval. And in this region, as I move from left to right, the graph is going down as well. So that's another decreasing interval. The graph is never increasing, so it never changes from increasing to decreasing or decreasing to increasing, so I won't get any humps or values. There's no maximum or minimum points. So I'm going to go to answer C through F now. It's decreasing in both intervals that I created. It's decreasing in the interval negative infinity to 7 and the interval from 7 to infinity. And neither one of those intervals was it ever increasing, so it never changes from decreasing to increasing. It's never increasing, and because it never changes from decreasing to increasing or increasing to decreasing, because it's always decreasing, I don't get any values for maximum or minimum points. Let me do C through E by hand now, and it's not particularly hard. It's real similar to do it by hand. I don't have to show that much work. So if 28 C through F by hand, which you need to do on the test, is show me a one-dimensional number line that has negative infinity on the far left edge, positive infinity on the far right edge, the critical number beneath also plotted on the number line. You need to create the intervals that are implied here. In each interval, you need to pick a test number. My left interval goes from a negative number to a positive number, so I'm going to test x equal to 0. My right interval is all positive. I just need to pick a number in that interval. I'm going to pick x equal to 8. And then I'm going to find f prime of 0 and f prime of 8 using the dy dx feature on my calculator. So now that I have the graph in here, rather than doing this by hand, you're allowed to go second calc dy dx, take your critical number, type it in. When I typed in 0, I got negative 0.204. I don't necessarily care so much what the number is, I just care about its sign. Because it's negative, the graph is decreasing in this interval. In the next interval, I'm going to go second calc, go down to dy dx, and when I plug 8 into the derivative, I get negative 10.001. I don't care exactly what the number is, I just care about the sign of the number. The fact that I got a negative number when I did this tells me the graph is decreasing in that interval. And when the graph doesn't change ever from increasing to decreasing or decreasing to increasing, you don't get any humps, you don't get any valleys. You have to change. Two intervals next to each other have to be going opposite directions to get a maximum or minimum point. When two connected intervals are doing the same direction, that doesn't produce a maximum or minimum point. So this graph is never increasing because none of the intervals say increasing. So when I go to do my answer, it matches up perfectly with the graph. None of the intervals were increasing, so I put none, or none I guess would be equivalently good. The two intervals where it's decreasing, it doesn't ever change direction, so I don't get a maximum or minimum. All right, so give 27 a go, and I'll move on to do 30. I'll do 30 and then maybe I'll make a part 4 to this video because it's already long enough. Alright, so for part A of number 30, find the derivative. I need to use the quotient rule. First thing for the quotient rule for number 30, I take the denominator, x plus 3, and next to it I write the derivative of x minus 6. The derivative of x minus 6 is going to go in that parentheses. The derivative of the minus 6 is 0 because it's a constant. The derivative of an x, because it's a first power term, has a derivative of its coefficient. Its coefficient is 1. And then I'm going to put minus, and then it's going to be the numerator, x minus 6, times the derivative of the denominator. So next to that x minus 6, I need to put the derivative of x plus 3. 3 is a constant. It has the derivative of 0. X is a first power term. It has the derivative of its coefficient. Its coefficient is 1. I could write that 1 after the parentheses, but it's going to be easier to write it before the parentheses. So that's the numerator of the derivative. The denominator is going to be the denominator squared. Now I'm going to clear the parentheses. X plus 3 times 1 is just, in the numerator is just x plus 3. And then minus 1 times the quantity x minus 6, minus 1 times x is minus 1x. Minus 1 times 6 is plus 6, and the denominator is x plus 3 squared. In the numerator, the x's cancel. I'm left with a 3 plus 6, which is a 9. So the answer for my derivative, the numerator is going to be 9. The denominator is going to be x plus 3 squared. That's part A by hand. To move into part B by hand to find the critical numbers, I find the value of x that makes the fraction equal to 0 by setting the whole fraction critical numbers. To find the value of x that makes the fraction or the derivative equal to 0, you set it equal to 0. And to find the value, so this is the equal to 0 part. And then to find the critical numbers that cause the derivative to be undefined, you take the denominator and set it equal to 0. So there's two kinds of critical numbers when your derivative is a fraction. There's critical numbers that make the denominator 0 or the fraction undefined, and there's critical numbers that make the whole fraction equal to 0. You get that by setting the fraction equal to 0. I'll cross multiply to do this. When I cross multiply down, I get 9 times 1, which is 9. When I cross multiply up, I get 0 times x plus 3 quantity squared, which is 0. This breaks down. The x's drop out, so there's no solution for this. When you set the x plus 3 squared or the denominator equal to 0, I'm going to square root both sides. I don't need the plus or minus on the right side because the right side is 0, and plus and minus 0 is just 0. Left side, the square root of x plus 3 squared is just x plus 3. The right side, you get 0. I minus 3 from both sides, and I get the only critical number is x equal to minus 3. So on my front page, I get the critical number of x equal to negative 3. And now I'm going to do the rest of C, D, E, and F using my calculator and then by hand. So for C through F, for number 30, I'm going to graph this. I'm going to focus on negative infinity, negative 3, and positive infinity on the x-axis. This creates the interval from negative infinity to negative 3 and the interval from negative 3 to infinity that I have to concern myself with. So I'm going to graph the function f of x equals x plus x minus 6 over x plus 3. Figure out what the graph looks like to answer my questions. So now I'm going to break out my calculator. Y equals clear parentheses x minus 6 divided by parentheses x plus 3. I'm going to zoom standard. Hopefully that window is adequate, but maybe I need to bump it up a little bit. I think that's probably standard, a good enough window. So the graph has a break, and negative 3, the graph doesn't exist there because it's outside the domain of the fraction. So the graph looks like this, more or less. It has this half, and it has this half that are broken. In this region right here, the region between negative infinity to negative 3, as I move from left to right, the graph is getting higher. So in this interval, I would say the graph is increasing because as I move from left to right in that interval, the graph is getting higher. Similarly, in this interval from negative 3 to infinity, as I move from left to right, the graph is getting higher. And it's also increasing in that interval. So I have two increasing intervals for my answer to problem 30. It's going to increase in the interval from negative infinity to negative 3. It also increases in the interval from negative 3 to infinity. It never decreases. So when I go to answer the part D, I could say it doesn't. There's no intervals or never. And because it doesn't ever change directions, you don't have a maximum point and you don't have a minimum point. Now I'm going to get all these answers by hand, and I'm still going to use my calculator a bit. So the by hand approach for 30 C through F, it's a one-dimensional number line as opposed to a two-dimensional graph. I put negative infinity and positive infinity at the edges, my critical number between, and this is what you're going to need to show on work, but you have to show us a little bit of work. So I've created my number line, one-dimensional as opposed to two-dimensional. By hand, I do a one-dimensional number line. In each interval, I need to pick a number. The left interval, all the numbers are negative. I can't pick 0. I'm going to pick negative 4. In the right interval, the first number is negative, the second number is positive. I'm going to pick x equal to 0. And now I'm going to find f prime of negative 4 and f prime of 0. And I hope for you to use your dy dx feature on your calculator. So to do f prime of negative 4, I go second calc, dy dx, type the number negative 4 in, and I get 9.009. The fact that that's a positive number tells me that in this region, the graph is increasing. When I do f prime of 0, second calc, dy dx, type in 0, I get positive 1. And again, I don't care so much what the number is. I just care whether it's positive or negative. and if I get a positive number in that interval, the graph is increasing. So those answers confirm with my graph, and when I show the arrows on this, it's increasing in both intervals, and in order to get a maximum or minimum point, the graph has to change in one interval from increasing to decreasing or decreasing to increasing, which it doesn't do. So we'll say that we have increasing in the interval negative infinity to negative 3, increasing in the interval negative 3 to infinity. It never decreases because I don't get any negative numbers out when I plug in a value critical number into my derivative. Because it doesn't change from increasing to decreasing or decreasing to increasing, I don't get any maximums or minimum points. So all these answers are correct, and this is the work that you need to show on your test to confirm that those answers are correct. All right, I'm going to pause the video. You should do 29. There's only going to be 2 problems in the part 4, but I feel like this is long enough now that I don't want to do this in this third part.